Today we enter a new chapter, chapter 4. The main topic in chapter 4 is energy and potential. The potential is also energy which plus 1 coulomb has. Today I'm talking about energy expended in moving a point charge in electric field. Consider the work done in moving q coulomb from point A to point B. This is point A and point B. The q coulomb and moving from point A to point B. There are many ways to move the plus q coulomb from point A to point B, like this path, many methods to move a plus q coulomb from point A to point B. Anyway, before we discussing this, we consider general case. We consider the object with mass m, and this is displacement vector, and this is force vector, and the angle between two vectors is theta. The work done exerted on the object with mass m is f vector the t vector. Same situation is applied to plus q coulomb. This is, instead of object we substitute plus q coulomb, and this is L vector. L vector means the moving vector of plus q, and this is force vector. This force vector is generated from electric field, so this is q e vector. So the work done for plus q coulomb from point A to point B, it means the work done is to move plus q coulomb from point A to point B. The moving method is many methods like this and many methods. Anyway, this is L vector. This is f dot L vector. However, generally speaking, the work done for plus q coulomb is against the electric field. It means this work must be recovered electric field, so we need minus sign in work done. So minus means it's against the electric field, that we have to move this plus q coulomb recovering the electric field. So this is minus q e vector dot L vector. However, we cannot find the work done directly, so first step is we have to find the differential work. This is minus q e vector dot dl vector. This dl vector is different from coordinate system, or we have another expression for this dl vector. So this is the first step. So next we can find work done and integration differential work. This is minus q integral e vector dot dl vector. The dl vector is different from coordinate system. So first case is in rectangular coordinate system, dl vector is dx ax vector plus dy ay vector plus dz az vector. So first step is find differential work is minus q e vector dot dl vector. This is dw is minus q. Electric field in rectangular coordinate is ex ax vector plus ey ay vector plus ez az vector. That dl vector is dx ax vector plus dy ay vector plus dz az vector. So it becomes minus q ex dx plus ey dy plus eg dz. So total work is integration dw, and this is minus q integral ex dx plus ey dy plus ez dz. This is the total work in rectangular coordinate system. And another expression to finding differential work is minus q E vector. The dl vector is like can be expressed like this, a dl vector. Then we have two methods to express the dw vector. Dw first is we express the dw in each component, and second method in magnitude and unit vector. By using magnitude and unit vector, we can express dw vector. The next is cylindrical coordinate. The L vector is d rho a rho vector, not d pi a pi vector, because dl is length. So pi component of the L vector must be length. So it must be rho d pi. So differential work. First step is we have to find differential work. Differential work is minus q E vector dot dl vector minus q. The electric field in cylindrical coordinate is E rho a rho vector plus E pi a pi vector plus E z a z vector. That the dl vector is d rho a rho vector plus rho d phi a pi vector plus dz a z vector. So we have another expression is the same, and this is magnitude of the L vector and a dl vector. So total work is integration dw. This is the total work in cylindrical coordinate. And next is spherical. In spherical coordinate, the L vector is the RAR vector, and theta component of the L vector must be length, so this must be RD theta. Also, the pi component of the L vector must be length, not angle. This R sine theta d pi. So dw is minus q. E vector is E R A R vector plus E theta a theta vector plus E pi a pi vector dot the L vector is the R A R vector plus R d theta a theta vector plus R sine theta d pi a pi vector. Also, we can express magnitude of the L vector a dl vector. And total work is integration dw vector. This is total work in spherical coordinate system. And potential is also work done when q is 1 coulomb, so minus initial and final. For example, plus 1 coulomb is moving point A to point B. The many methods to moving from point A to point B anyway. And this is initial point is A and final point is B. And the q is 1 coulomb. So minus integral E vector dot dl vector. This is called work done when q is 1 coulomb. Is simply we called it potential. This is potential. Potential difference between A and B. This is potential. And we take an example. E vector is given, and we find differential work in moving 6 nanocoulomb charge. Distance of 2 micrometer from 2.3 in direction of this vector. And dw, the finding dw is our purpose, and this is minus q E vector dot dl vector. So we have already known q vector, plus q is this 6 multiplied 10 to the power of minus 9 coulomb. E vector at minus 2.3 is 1 over z square 8xyz ax vector plus 4x square y ay vector minus x plus z ay vector 4x square y az vector at 2 comma minus 2 comma 3 and 1 over 3 square 8 multiply 2 multiply minus 2 multiply 3 ax plus 4 multiply 2 square multiply 3ay minus 4 2 square 2az vector. It can be 1 over 9, and this is 16 minus 6 and minus 96 ax vector. 4 4 6 plus 48 ay vector. 4 4 2 16 multiply 2 is 32. This is y is minus 2, not 2 is minus 2 az. So minus 2 plus 32 az vector. And dl vector is dx ax vector plus dy ay vector plus dg ag vector, because electric field is expressed by rectangular coordinate system. And second expression is the a dl vector. We cannot know this information, so we use this. Magnitude of dl is 2 multiply 10 to the power minus 6, and this is unit vector or not, we don't know, so we check this is a unit vector or not. Minus 6 over 7 square plus 3 over 7 square plus 2 over 7 square. A square root, denominator is 49 and numerator is 36 plus 9 plus 4. Numerator is also 49. This is also 1. So this is a unit vector. So we can, this is minus 6 over 7 ax vector plus 3 over 7 ay vector plus 2 over 7 az vector. So we can find differential work at point P. And differential work is minus 6 over 10 to the power minus 9 multiply 1 over 9 and minus 96 ax vector plus 48 ay vector plus 32 az vector multiply 2 multiply 10 to the power of minus 6, and unit vector is minus 6 over 7 ax vector plus 3 over 7 ay vector plus 2 over 7 az vector. We can calculate this. The result is minus 149.3 multiply 10 to the power of minus 15. Unit is joule, because this is the work done, the energy. So this is minus 149.3 femco joule. Femco is the power of 10 to the minus 15. So this is the answer for this question. So today we discussed about the work done by moving plus q coulomb from point A to point B. And this work done when the q is plus 1 coulomb is called the potential difference between A and B. And we take it, we start one example. Thanks for listening this video, and see you next time. Bye bye.